Having looked at linear functions and the definition of linear function, there's a nice check that we can now impose. Our last example looked at the function 3x plus 1 as the transform. We found that was not linear. And part of this hinges on this plus 1, this shift. And a nice corollary to that is that when we have what we call a linear transform in linear algebra, anytime we transform between two vector spaces, the zero vector input from V has to map to the zero vector in W to be a linear function. And we know why this is the case because linear functions, linearity requires that if I have an alpha times L, let's do it the other way, L of alpha times a vector V has to equal alpha times L of V. That's one of the properties. But if alpha equals 0, so scalar, remember alpha is some element of the reals, and V is some element of our vector space. But if alpha equals 0, what does this turn into? It turns into L of 0 in the V vector space is equal to 0 times L of V. This is an element of the W vector space, the output space, but 0 times it is going to be 0 in the W space. So L of 0 in the V space has to equal 0 in the output space. If we don't have that, we're never going to satisfy this scalar multiplication criterion. And that becomes a quick check. If we run 0 from our input space in through our function, we don't get 0 back from our output space, then we know right away it's not a linear function because it won't satisfy this requirement. So we can just do a quick check and find L of 0, 0, 0, because 0, 0, 0 is an element of R3, which is equal to the input space, and I should have actually said that here. That L here is mapping R3 to R2. And this thing here is the zero vector in R3. Well, L of 0, 0, 0 is equal to 0 plus 1, and 0 plus 0 and 0. This is not equal to the zero vector in R2. And so right away, I can tell that this function, L of x, y, z, is not a linear function. And that's fine. It's not a perfect test, but it's a quick and dirty one. If a function doesn't satisfy L of 0 equals the 0 in the output space, then right away, you're done. Now, a counterexample to this would be one we actually saw earlier. If we took the transform to be mapping from the reals to the reals, and our function was that x maps to, let's call it L of x maps to the square root of the absolute value of x, then for this case here, L of 0 actually is equal to 0, but that's not enough to rule it out. But still, L is not linear. So specifically, if we get this mapping, then L might be linear. Whereas if we do a mapping of the zero vector, we don't get the zero vector in the output, then L is definitely not. Definitely not linear. In this case here, what do we do? Oh, we have those two tests. We need to use both linearity tests. We have to go review those specifically. The sum and the scalar multiplication. All right, let's do something a little more exotic now. So determine whether the definite integral over a fixed interval of AB is a linear transformation. So how would we even start defining that? Well, what we're going to do is take functions. So let's start with C infinity, but some set of functions. And when we integrate that over a fixed interval, well, what does that mean? That means I'm going to take my function f, and I'm going to integrate it from a to b. And from calculus, we know that gives us a single value. It gives us a number. So that's going to map to the real values. So the definite integral is a transform, can be thought of as a transform of functions to the real line. And what we can do now is check the criterion. So we're going to check the criterion 1 for linearity. And that is specifically that if I transform some function 1 plus some other function 2, we get the transform of them separately added after the transforms. This time we'll start with the left-hand side, or consider the left-hand side of that equation, which is the integral from a to b of f1 plus f2. So f1 plus f2 of x dx. But that, we know in terms of function definitions, that is the same as f1 at x plus f2 at x. So we're going to have f1 of x plus f2 of x dx. And that, because the linearity of integrals, we know we can split integrals at plus signs, and so we can rewrite that as the integral from a to b just of f1 of x dx plus, all that in brackets to make it obvious that it's a very different calculation, the a to b integral of f2 of x dx, close bracket. And then, hey, that is what we mean by the transform of f1. That is L of f1. And this, not too surprisingly, is the transform of f2. And so we can start with this form of our transform, and we can do some work using the rules of integrals and functions, and get to the alternative that is L of f1 plus L of f2. And so the integral on a fixed interval satisfies this criterion of, the first criterion of linearity. Of course, that leads us to the second criteria, which is, how do I phrase that here? Criterion 2 for linearity is that we have a scalar multiplier that can move in and out of the function, that L of alpha f is equal to alpha times L of f. And hopefully you're thinking that, wait, I know I can pull constants out front of integrals. That's exactly what we're going to do. So the left-hand side is, we're nominal reals, and f is an element of C infinity. I should put that back here as well for f1 and f2 elements of C infinity. All right. So the left-hand side here is L of alpha f, and that is equal to the integral from a to b of alpha f of x dx. And again, we have definitions of what we mean by scalar multiples of a function. This is the same thing as alpha times f of x. And once we've done that, hey, if I have a constant and I have an integral, I can move the constant out front of the integral. And then we recognize that this a to b f of x dx is exactly what we mean by the transform of f. And by satisfying those two criterion, we can say that L, which is L of f, which is equal to the integral from a to b of f of x dx, is a linear function or linear transform. I'd say transform here. We're taking a function and turning it into a scalar value, so it feels somehow deeper than just a function, or it's a bit more meta. So yeah, a linear transform here.